Hello and welcome. Today we're going to look at a nice mathematical expression for our following sum. We're looking at the sum of the 0th to nth derivative of a function which is at least n times differentiable. So, how are we going to approach this problem? Well, the first thing that we're going to do is to set our summation equal to y. This will simplify our equations. Next up, we're going to differentiate both sides. By doing this, you can actually take the differentiation on the left side inside the sum, as differentiating is a linear operation. Now we're looking at our summation. As we're saying that we take the kth plus 1 derivative of a function, we can also state that our sum starts at 1 and ends at n plus 1. This will mean that the derivative of y actually is our summation, but shifted up one term. Now we're going to make the following observation, namely that our starting sum of differentiated functions minus the derivative of this sum is equal to y minus the derivative of y. This, of course, is a very trivial observation, but it will help us later on in this video. Now we're actually going to look at what happens if you subtract those two sums. Well, you see that actually only the first term of 0 and the last term of n plus 1 are left over, as the other terms will cancel out. This means that y minus y prime is equal to the function fx minus the nth plus 1 derivative of this function. Now, this is simply a first-order differential equation, and we can solve this. First, we're going to find our integrating factor. Now, I'm not going to explain how we are going to find our integrating factor, as that is beyond the purpose of this video, but for those who know how to solve first-order differential equations, you will see that it is indeed minus e to the power minus x. For those who don't know how to solve first-order differential equations, it is just best to check whether the last row is actually true. There it states that the derivative of y times e to the power minus x is equal to, between brackets, the nth plus 1 derivative of a function minus the function itself times e to the power minus x. And you can double check this. Now we have a simple differentiation problem. And by integrating between two certain boundaries, which are picked arbitrary, we can actually solve for our summation. So the boundaries are taken arbitrary, 0 and x, but you'll know that you can expand your function, compress, and shift it, so it doesn't really matter. So now we're going to fill in our boundaries from the left side. And if we'll do that, we'll find the following. Namely that y of x times e to the power minus x minus y of 0 is equal to the integral we have on the right side. Now, this is very interesting, because if we would know y0, then we would also know yx. Now, we can first do some arithmetic and solve for yx. And that's what we'll do. And here we have an expression for yx. But now remember that yx is our summation. Thus, we found an expression for our summation. Now this, of course, is very interesting, but I want to show you something else which is even more interesting. If we'll leave it at this, then we have a very useful expression which can help us solve tricky integrals. And one of the more tricky integrals that I would like to show you is the following integral. This is the integral from 0 to x as x goes to infinity of z to the power n times e to the power minus z dz. And we'll want to prove that this is equal to n factorial for all natural numbers of n, including 0. Now, how are we going to solve this integral? Well, we'll just use the mathematics that we've learned. Now, if you observe that these two parts are equal, since if you would differentiate z to the power n plus 1 times, you'll get 0, you can express it in our summation. Now, this looks very gibberish and it might be hard for you to understand, but we're just plugging in the function, or rather the formula that we found previously, and we're just doing some mathematical operations to make it look nice. So I hope you can follow this, but it's not really that hard, to be honest. It's not the hardest part of this video. Now we're going to look at the value of our first summation and the value of our second summation. And if you look at the first summation, you'll see that it will always be 0, except if you differentiate your function n times, because then it's z to the power 0, which gives 1 always, and you differentiate it n times, so you have n times n minus 1 times n minus 2, on and on until 1. And this, of course, gives us n factorial. And on the right side, you have x to some power divided by e to the power x. But you know that e to the power x always grows faster than x to the power something, which will mean that that sum will approach 0. So we can just cancel it out, and in the end, we get n factorial. So this is a very nice way to prove that our previous integral, which was otherwise very hard to solve, is actually n factorial. Now, with that being said, I want to solve you the following integral. I will make a video about solution on a later point, and I hope you enjoyed this video. Now, thank you for watching. This is my first video and I hope it won't be my last. I have more videos coming up about mathematics. I mainly want to show original content. I have some formulas which I figured out myself, which I think you'll find very interesting. So keep up to date and I'll put out some more videos if people are interested. Other than that, I think I will also do different videos, not only about mathematics, but also about physics and biology and perhaps some ethics. And hopefully maybe a podcast. We'll have to see. But with that being said, this is my first video. I hope you enjoyed this. Consider subscribing. You don't need to, honestly. But if you like this, you're very welcome. Thank you for watching and goodbye.